In this video, we start from a basic geometric intuition for the continuity of a function at a point, and then we use that intuition to develop a definition of continuity in terms of limits. Finally, we're going to do a few examples where we test the continuity of a function and we classify the discontinuities using our definition. So what's the basic intuitive geometric meaning of continuity? So we're going to say that a function f of x is continuous at x equals a if we don't have to lift our pencil to draw f of x through x equals a. And that's really it. So as we watch this curve being drawn through x equals a, of course it's a nice smooth curve with no gaps of any kind. We don't have to lift our metaphorical pencils, and we say that f of x is continuous at x equals a. So now we're going to figure out how to define continuity at x equals a more precisely by using limits. And we're actually going to get this done by looking at all the ways f of x could fail to be continuous. So check this function out. It's definitely not continuous at x equals a because we have to lift our pencil to draw the two different branches. And this is actually a pretty realistic example. I made it by plotting the function 1 over x minus a. So there's a denominator there approaching 0 as x approaches a from the left and right. So we see this familiar behavior of diverging to infinity, and we have a vertical asymptote. So in symbolic terms, why does f of x fail to be continuous here? I do have other complaints about this function, but I want to focus on the simple reason that a is not even in the domain of the function. If a isn't in the domain, in other words, if f of a isn't even defined, then of course we have to lift our pencil to skip that point. So this is our first clue for developing a symbolic definition of continuity. F of a better exist, otherwise we've got a problem. And just a side note here, this particular type of discontinuity that we're looking at is called an infinite discontinuity, simply because we have those infinite limits occurring at the point of interest. Next, we look at a different kind of problem. We have to lift our pencil to draw this one because we have to cross a finite gap. So f of a is well defined. In fact, if you can see the grid on your screen, f of a is 2 in this picture. But there's a sudden vertical jump at x equals a, where this function jumps from a height of 0 to a height of 2. Now, to get a handle on this one symbolically, we're going to blame that vertical jump on the fact that the left and right limits don't agree here. As x approaches a from the left, we're getting close to a value that's different from what we get when x approaches a from the right. So that's our second rule for what it takes to be continuous. The left and right limits better agree, and by the way, that means the ordinary limit exists. Remember, the ordinary limit, the limit as x goes to a of f of x, exists if and only if the left and right limits both exist and they agree with each other. And by the way, this particular type of discontinuity in the picture is called a jump discontinuity. Finally, we look at a type of discontinuity where we just have a single hole poked in the function. So I've made it so that f of a actually exists here, but it's separated from the rest of the function. And we also see that the left and right limits exist and they agree with each other, meaning f of x gets close to the same value from the left and right sides of x equals a. So how do we articulate the problem that forces us to lift our pencil here? The problem is that f of a isn't the same value as the limit as x goes to a of f of x. All right, so we say that f of a needs to agree with the limit as x goes to a. And writing that all down mathematically, there it is. The limit as x goes to a of f of x better be equal to f of a to prevent this sort of discontinuity. And just a side note, of course, this kind of discontinuity gets a special name. This is called a removable discontinuity. Now, this statement that we've just written down, that the limit of f of x as x goes to a equals f of a, is way more clever than it first appears. This is actually going to be our formal definition of continuity at a point. So just going back through all the problems that we just covered. First, we had a type of discontinuity caused by f of a not being defined. Well, by writing the f of a in this definition, we are implying that f of a exists. So that type of discontinuity has already been ruled out. In our second type of discontinuity, that was a jump discontinuity. That was created by the left and right limits not agreeing with each other. But if we look at the left-hand side of our statement here, we're saying the ordinary limit of f of x as x goes to a exists. And that automatically implies the left and right limits agree with each other, and that rules out jump discontinuities. And finally, the fact that the limit as x goes to a of f of x is equal to f of a, that prevents us from having removable discontinuities. So there it is, one simple statement about limits that guarantees you don't have to pick up your pencil when you draw a function through x equals a. All right, so before we get into some examples, I want to cover a quick guide to classifying discontinuities. So we're going to start with this statement. Suppose that f of x is actually discontinuous at x equals a. How do we tell what type of discontinuity we're looking at just based on the symbolic mathematics here? So first, given that we already know f is discontinuous at x equals a, we're going to call that a removable discontinuity if the ordinary limit as x goes to a of f of x actually exists. Now remember, saying the limit as x goes to a of f of x exists automatically means that we're talking about the left and right limits both existing and agreeing with each other. So it's a removable discontinuity if those left and right limits agree with each other, and yet the function is still discontinuous. In other words, it's something like the picture on that last example that I did. Okay, next, when do we have a jump discontinuity? That happens if the left-hand limit doesn't agree with the right-hand limit. That creates a finite vertical gap in the function that forces us to lift our pencil. And then third, we're going to classify some discontinuities as infinite. And that happens if the left or right limits yield a plus or minus infinity when we take those limits. So this typically would happen in a rational function as the denominator is approaching 0. You get a spike to infinity and a vertical asymptote. So I've got 3 examples prepared, and here's the first one. We're asked to find and classify the discontinuities of the function f of x equals x squared minus 9 divided by x minus 3. Now the first thing we want to do here is simplify this function so we can get a better grip on what we're looking at. And to do that, we're going to factor the numerator. That's the difference of 2 squares, x squared minus 3 squared. That should factor into x plus 3 times x minus 3. Then in our denominator, we have an x minus 3. That factor of x minus 3 cancels out, and our function has simplified to just x plus 3. Now we still have to keep in mind that the original function f of x was not defined at x equals 3 because that causes division by 0 in that original statement of the function. So we could write the domain down in interval notation, but just to be less formal about it, it's all real numbers provided x is not equal to 3. That has to be thrown out of the domain. And before I finish officially classifying this discontinuity, I want to take a look at the picture of this function. When we graph it, we can get almost every point on the graph right by just plotting f of x equals x plus 3, which is a line with slope 1 passing through a y-intercept of 3. But we have to poke a hole in this function when x is equal to 3 because that's not in the domain. So this one gets classified as a removable discontinuity. And we're going to say there's a removable discontinuity at x equals 3. Again, the definition of a removable discontinuity is that the ordinary limit exists at that point, and yet it's still a discontinuity, meaning that that limit doesn't agree with the value of f of a. Well, in this case, f of 3 isn't even defined. So we have the limit being well defined, f of 3 isn't even defined, and we end up seeing that as a hole in the graph, which clearly forces us, of course, to pick up our pencil while we draw the thing. All right, in our next example, we're given a piecewise defined function. We're told that f of x is equal to x when x is less than 2, but f of x is equal to 3 when x is bigger than 2 or equal to 2. So f is going to be continuous everywhere except for possibly at this cut point, x equals 2. So that's really where we're doing the test. And to investigate the continuity here, we're going to look at the limit from the left and right side as x approaches 2. So the limit as x goes to 2 from the left-hand side of f of x. Well, if I'm approaching 2 from the left-hand side, that means x is less than 2. So we're going to follow this rule. F of x is going to be equal to x on that branch of the function. And there's nothing tricky going on here. As x gets close to 2 from the left, x gets close to 2. The limit is equal to 2 here. Now when we investigate the right-hand limit, we take the limit as x goes to 2 from the right. Well, now x is bigger than 2, and that means we're going to be on this branch of the function where f of x is equal to 3. And of course, the limit of a constant is just that constant. So what we've discovered here is that the left and right limits are disagreeing with each other. And of course, that's going to create a vertical gap in the function. In other words, this is a jump discontinuity. And we can say there's a jump discontinuity at x equals 2. So let's take a look at the picture here just to verify the things that we've done symbolically. So there's our function. My left-hand branch is just f of x equals x. In other words, a line of slope 1 passing through the origin. My rightward branch is just f of x equals 3. In other words, y is equal to a constant 3 there. And we see an open circle at the end of that tilted branch because we're only following that rule when x is explicitly less than 2, and a closed circle on the upper branch because we're following that rule when x is bigger than or equal to 2. And there's our finite jump in the graph, verifying that we have a jump discontinuity at x equals 2. Finally, we're asked to find and classify the discontinuities of a rational function f of x equals 1 over the quantity x minus 3 all squared. Now clearly x equals 3 is the interesting point here because that would make the denominator equal to 0. So I know that x equals 3 is not even in the domain of this function, so we're definitely going to have a discontinuity there. Well, then I think about what happens in the limit as x goes to 3 from the left and right hand sides. And of course the denominator is becoming vanishingly small here as x approaches 3 from the left. And in fact, 1 over x minus 3 all squared is staying positive the entire time because even though x minus 3 is going to be slightly negative, I'm squaring that guy and I get a positive result. So I'm approaching a denominator of 0. I have a very, very small denominator while the numerator stays finite. This gives me an infinitely large result as I approach this problematic value, and it comes with a plus sign. So I have a limit of positive infinity. What about when x is slightly bigger than 3 and approaching 3? Again, I'm going to have a positive result for 1 over x minus 3 all squared. And the denominator is approaching 0 as the numerator stays finite. All the same arguments there. It should approach positive infinity as I approach from the right as well. And of course, anytime you see one of the one-sided limits approaching plus or minus infinity at a discontinuity, we're going to call that an infinite discontinuity. All right, so we have an infinite discontinuity at x equals 3, and we'll take a look at the picture of this function real quick. And there's our rational function spiking to infinity as we approach x equals 3 from the left and from the right, just verifying that we have this infinite discontinuity, forcing us to lift our pencil as we draw the function. In the next video, we're going to use our new definition of continuity to prove that all polynomial and rational functions are continuous on their entire domains. I'll post a link to that video at the upper left, and I'll see you there.